Well, it looks like we're at that normal time. Welcome back. For today's class, we're going to continue on through section 4.3. We're currently on example 2. It's a pretty long section. We spend a lot of time just to land on example 2 last night. And then we're going to get back into a familiar topic, working with indeterminate forms. And this is always a weird word when you see it the first time. It's a weird name, rather. L'Hopital's rule is how that's pronounced. Here we're going to be taking specifically a look at limits at infinity. And if we have some extra time, we might open up that section. The syllabus had us on target for finishing 4.7 this week, but seems like it was getting a little too aggressive. So we'll make up some time and work on section 4.7 when we come back Monday next week. Also, the bigger thing we have going on as well for the announcements is the exam 2. I'll begin grading that tomorrow morning on Friday. I'll get caught up on grading homework first, then grade the exam 2. And my goal is to have that finished sometime on Friday. If I do get behind, I might do it completed on Saturday morning, but I usually try not to let grading spill into the weekend if I can help it. Well, that's where we're at so far. Any questions at all before we begin? Okay, let's jump in. Hopefully others jump in as well as we get started, but I'm glad you made it today. So we're on midway through example 2, but I rewound the notes a little bit back to this page just for a quick refresher before we jump back into the algebra. For our definition that we're looking into, concavity, we're told if the graph of a function f lies above all of its tangents on an interval, then the curve is concave up on that interval. So we said concave up on approximately this interval here, because if you draw tangent lines, let's draw a new one for emphasis, say one tangent line right here. The graph, the one in black, is always above the tangent lines in this particular interval. So for that interval, we have concave up. And if we go, say, to the other end, right around here, anywhere we draw a tangent, they're not always easy to draw. So let's draw one, say, right around here. If we draw a tangent line going through that value, where the red dot is, the curve will lie below the tangent line. That means if it lies below all the tangent lines in that new interval from about here to here, we say it's concave down. And then something happens from around this point down over to this point where we're now concave up from where we were concave down. Concavity seems to switch. And a point on the graph where the function is continuous, where concavity changes, is the so-called inflection point. So this is what it looks like just purely graphically, trying to find the intervals on concavity, the inflection point. Finding these exactly is really, really hard. I don't know exactly what those coordinates are, but now if we use calculus, we can determine the exact interval, we can determine the exact inflection point if it exists, and well, that's the wrap up of the idea of concavity. It has a bigger role. It's going to help us find local minimums, local maximums, but we're studying it for its own sake first. Well, any questions at all with the refresher on concavity? Okay, now to actually find these intervals of concavity, where it's concave up, concave down, and the inflection point, we use the concavity test. And it's kind of an amazing test in a certain sense. It just relies on the second derivative specifically. If the second derivative is positive, we have concave upward. If the second derivative is negative, we have concave downward. And that's what we were working on in this example too, right here. We're trying to find the intervals of concavity for that particular function. It's a complicated one, a natural logarithm composed with a degree 4 polynomial. In order to use this concavity test, step 1 is compute the first derivative and then simplify it as much as possible. Step 2, compute the second derivative. And then we took all these steps because we had to also simplify this as much as possible. And this is where the algebra landed. we have to set it equal to 0 to find out where the second derivative is positive, where it's negative. So these are the 3 cut points. We found that by observing if you put 0 here in the numerator, the equation balances as 0 equals 0. There's no solution here. The smallest 9 plus x squared ever gets is 9 when you choose 0 for x. But here we had 2 other solutions, -3, +3. And so we grab those, drop them down into the numbered line. And now we're at the point where we're about ready to use the concavity test. So let's scroll down to maybe about this part. Here's the test for easier reference. Our second derivative is here, and now all we're doing is testing intervals. We mentioned before last class, this is almost completely analogous to how we did the increasing, decreasing test. The only difference was we're using the first derivative, not the second derivative here. So this is where we left off. Sorry for splitting this problem in half across one day to the next. Any questions at all, folks, for the getting caught up on this problem here? Okay, so here's where we now need to test intervals, just like we did on example 1 for the increasing decreasing test. I'll use maybe this color here to indicate a test point we're using. We need to test any number here that's convenient that's less than -3. So I'll put here testing values. And let's pick something nice like -4. We don't have to go too crazy. We're going to compute the second derivative of -4. And it's kind of a mouthful to say this all out at once, right? It's not as bad as it seems, because if we're only determining if it's positive or negative, really all we need to know is what the sign is for every single one of these factors. So there's a couple ways to do this. You could say there's a positive sign here, because if you square -4, that's a positive 16. This is absolutely positive, because if you square something and then add 9, it's more positive than x squared itself. It's going to be that value plus 9. Really, the only things that actually influence this are what happens to those factors. Everything else here is just always positive because of the power 2 on this one, power 4 on this plus 27, or the power 2 on that just forces it to be positive no matter what number you throw in. As long as you're not throwing in, say, a 0, then this is always positive as well. So it only really just boils down to there. So if you focused on just those 2 factors, that's enough to do it. It looks a little bit weird on the notes because we said f double prime at -4. So this is mainly just emphasizing that's a shortcut if you wanted to take it. But just for the sake of the notes, let me write it out this way just to show you what you would typically do. This is just a really long one. This would be 4 by -4 squared times 9 plus -4 squared. And then here's where it really matters. 3 plus -4 gives us a -1. Then this is going to be 3 minus a -4. The double negatives just gives us a positive 7 altogether. The denominator, likewise, it really doesn't matter. We just want to know if it's positive or negative. This is guaranteed to be positive. But I'll write it down just again for the sake of the notes. That's -4 power 4 plus 27 to power 2. And even though we have negatives here, it all boils down to those 2 factors. We have a negative times everything else that's positive, numerator and denominator, which means the whole entire thing is negative. We don't need to put it into a calculator and find the exact value. We're just trying to determine positive or negative. We found, oh, wrong color. We found it's negative. F double prime is less than 0 on that interval when we throw in a -4. And so on this entire interval from -infinity to -3, f double prime is now less than 0, which means we are concave down. And I'll use, just for shorthand, CCD to stand for concave down. So that's 1 down, 3 more intervals to test. But again, same kind of idea as we did in example 1 for increasing, decreasing. Only difference is you're using the second derivative. So it's rinse and repeat. Any questions so far to this stage? Okay, for the second interval where the red dot is, I would say the most convenient number to use might be a -1. So let's pick that value, compute f double prime a -1, which means throw -1 everywhere. Let's make a prediction. If you put -1 here, that's going to be a 2, and a -1 here, that's going to be 4. That's just going to be positive altogether. So again, that's a really great shorthand. Look where the sign can change, so you don't necessarily have to copy everything. So if you like that shorthand, that's completely fine for homework and exams. For the sake of the notes, like I said before, let's plug it all in so it doesn't seem like if you came back here, some weird mystery happened and we just made a conclusion. So plugging a -1 into this whole function would just give us 4 times 1 coming from -1 squared. This would just be a 10. This would be a 2 times 4 from this part. Guess it's not so bad to plug it in. We put a -1 here, that's just going to be a 1 plus 27, so that's 28 squared. And as predicted, that is definitely bigger than 0. So we have positive here. Positive means when the second derivative is positive, we're concave upward. And I'll use CU just as a shorthand for concave upward. F double prime positive, concave up. And then on to the next one. It gets kind of methodical as you go through this. And there's a lot of patterns you might notice that are sometimes bona fide patterns and sometimes they're non-patterns. Sometimes you almost expect the sign to switch on every single one, but it's not always true. That power 2 there for x is where we got one number 0. Because the degree for that factor is even, it's not going to switch on us. My prediction is positive again here, concave up. So watch out for those kinds of things. Sometimes the safest thing to do is just test it out to be really careful. So test another value, f double prime at 1. This is just like before. This would become 4 times 1. This is 9 plus 1, really, so times 10. This would be 4 times a 2 from this one. The denominator is still 28 squared when we plug a 1 in for x. And so it's still positive. Kind of weird, right? That only happened because of the power 2. We're going across the 0 of multiplicity 2 is what we might say in a pre-calculus 1 class. That gave us positive again, f double prime, positive, so concave up. And last one to go through. We made a prediction on this one. We have a cut point at 3. It came from this one. The power here is a 1, which is odd. Now, if it was power 2, which is even, my prediction is positive again. But because the power is 1, it has an odd multiplicity, I'm expecting the sign to flip on us. It should be negative, but best practice sometimes is just test it out to see if that really in fact happens. We're plugging a 4 in next. So f double prime at 4 is going to give us 4 times 4 squared. And this is 9 times 4 squared. I guess that's 9 times 16 for a 25. Then this will give us a 7. The next factor is going to give us a -1. The denominator is 4 power 4 plus 27 squared. That's just a fancy number that's completely positive. Forgot to highlight those two. But once again, this is the only part of the function that can cause a switch in the sign. And we have a negative sign in there. The whole thing is now negative. So that matches the prediction. F double prime in this region is less than 0, which means concave down. So we have a sign chart. We have some information here. We still have to write out our full conclusion. But any questions at all, folks, with the full write up for concavity? Oh geez, what did I do? Let me see if I can fix that. Okay, there we go. So now, final thing to say is the function f, I'll just say briefly, f is concave. I'm just going to go left to right. So starting with concave down, on the interval from negative infinity up to 3, we use an open parenthesis there because, or excuse me, up to negative 3. Forgot my sign. We're using an open parenthesis. It cannot be a bracket because we don't have any concavity at negative 3. That looks like where an inflection point might exist. This is where concavity changes. So we take that and go union. Also concave down on this opposite end from 3 to infinity. And is concave up. Concave up goes from negative 3 to 0. At 0, where the second derivative is 0, that has no concavity there. Then it becomes concave up again. So we have to be kind of careful on this one. It's not concave up from negative 3 to positive 3 because 0 is excluded on that one. That becomes kind of a slight technical issue right there. So the only correct way to write this is concave up from negative 3 up to 0, then union starting at 0 but not including it, beyond 0 up to 3, it's concave up again. So that's the concavity on this curve. Well, we are essentially done. Last thing to do is take a look into the inflection point. But really the hardest part of this whole problem is getting to there sometimes. Sometimes the second derivative is just a lot of algebra. Once we have that, we're just redoing what we did with the increasing decreasing test and stating an overall conclusion through this concavity test below. So last thing we need to do is find the inflection points on the graph of that function f. Any questions at all, folks, to this stage? Okay, now another thing that's tricky about this is there's really 3 functions on paper. There's the second derivative. Here it is in its full nastiness, its full glory, I guess you could say. Here's the first derivative, definitely a nicer looking function. And the third function is the original. When we talk about concavity and we talk about inflection points, we're talking about the graph of the original function, that one there. So when we do the last part, we return back to the original function. Let's put it down here for reference. We're talking about the inflection points on the graph of f. And a point of inflection is a point on the graph where concavity has changed. From our sign chart, there's going to be an inflection point here, but not at 0. Concavity didn't change there. It stayed concave up on the left end and the right end. But it did change here. It went from concave up to concave down across 3. So we can now say the inflection points, let me change the color here. The inflection points because they're points, we really have to write them in as points. They go, first let's grab this one where concavity changed. It'll be negative 3, f at negative 3. And the second inflection point where concavity changes is here. What's a point on the graph of f, so we have to give the ordered pair 3, f at 3. So if we do f at 3, we're plugging 3 in here for the value of x, raising it to power 4, adding 27. That sounds like a calculator job. 3 power 4 plus 27 becomes 108 altogether. And same thing with negative 3 power 4. I don't know why I did the positive first, but it's the same value, either positive or negative. We get 108 for the inner part. So the whole thing becomes natural log 108. So the inflection points are at coordinates negative 3, natural log 108, and positive 3, natural log 108. So that's the whole story for concavity for this particular function here. If we plot it, let's take a look at what this all looks like. F of x is natural log x power 4 plus 27. Here's our curve. It's kind of a weird one. And what did we say? Concave up between -3, +3. And yeah, it looks like it would be concave up in this region. If you throw down a horizontal tangent line right at the 0, 3.29 point, the curve lies above the tangent. But now we know through calculus that concavity changes at -3, changes at +3. And if you put a tangent line here, the curve would lie below its tangent. We happen to know the exact inflection points are these down below. That's not something I could determine by visual inspection, so calculus is needed to make that conclusion. Well, that's the, again, whole story for concavity so far. Any questions at all walking through this full process? Okay, probably the next natural question is, sure, concavity is interesting. It influences the shape of the curve. But a natural question is, what is it good for, really? And I think this is a good graph to go right back to explain. When we look at a graph like this one, let's maybe screenshot it. Notice what this is providing for us. In a region where it was concave down, we have a local maximum somewhere in that region. In a region where it was concave up, we have a local minimum somewhere in that region. Turns out that's not a coincidence at all, which is kind of a remarkable fact. And this becomes, this whole content here, the idea behind the second derivative test. So now we have two derivative tests, and they're both for the same exact purposes, to find a local minimum, to find a local maximum. We'll be returning to these tests when we go to our optimization section, section 4.7. So this is really just our first look at it before section 4.7. The second derivative test, like we mentioned, it feels like the conclusions are backwards, but they're really not. If the second derivative is positive, that means the curve is concave up. So we have concave up here, second derivative is positive, but you have a local minimum. And we actually know where the local minimum is, because when we take f prime at c equals 0, what we're doing is we're saying that c is the critical number. We have a critical number right here. That's where f prime at c would be 0. So right at a value 2. And that's also a local minimum. It's concave up in that region where the second derivative was positive. And then at the same time, we have another spot where f prime at c equals 0, another critical number. A critical number is where the derivative does not exist, or where the tangent line is horizontal, and it's horizontal again right here at value 1. And this is the function that we did on example 1, so our conclusions go exactly the same. In this region, we have a local max. We also had that it was concave down in this region, and concave down just means second derivative negative. So this is always kind of weird. A negative there, going with a maximum for the second derivative. A positive here, going for the minimum in the second derivative test. So watch out for those reversal of expectations. It can kind of throw us off whenever we're doing this kind of problem, particularly in an exam situation. One thing that's nice about the second derivative test is if the second derivative happens to be a fast computation, it's faster than the first derivative test because you never have to do the following for the second derivative test. You don't have to do this stuff. You don't have to come up with a sign chart, test different values in the first derivative. You just go immediately to a conclusion. So if you can skip all this stuff in the middle and just go right down to local max, local minimum, then that really makes the second derivative test really worth it. So that's where this test shines. Where it doesn't shine as brightly is right here. Part C says, if you find the critical number is 0, but the second derivative happens to be 0, there's no concavity there, and the picture here just doesn't work any longer, the test has failed. Not in the sense that there isn't a maximum or there isn't a minimum. What it means is we don't have any information about what's going on in that critical number. It could be a local max, it could be a local minimum, or it could be neither. And how do we find out which situation it is? We go back to the first derivative test, which is kind of unfortunate. The first derivative test can resolve this if our second derivative test ever happens to fail. So last thing we'll do on this notes is do a full walkthrough of the second derivative test. But any last questions at all, just looking at the information here sketched out? Okay, let's give the second derivative test a try. Here it is again, just for easier reference. And now we have a particular function we're going to take a look into. Another logarithm it looks like, but different function for sure. We want to use the second derivative test to find all local maximum, all local minimum values of that function. Pretty weird one, x times the square of natural log of x. Well, here's the statement of the second derivative test, but the flow of actually using the test is a step-by-step procedure that looks more like this. Step 1, what we want to do is find critical numbers. A lot of the procedures in this chapter when it comes to optimization is about those critical numbers. So step 1 is to find critical numbers. Really, we're just solving that equation where the derivative is 0 or does not exist. So compute f prime at x to get started, which means we're differentiating that function. That's a pretty tricky derivative in its own right. That one's going to require product rule. So let's carefully run through product rule. In the product rule derivative, we take the derivative of the first factor, which is x. That gives us a 1, and multiply it against natural log x squared. Then add, now copy x, multiply it against the derivative of natural log x to power 2, but that's a composition of functions, so it's product rule and chain rule, which makes it a good refresher problem just on its own for doing the first derivative on this. When we do the chain rule derivative for a function like this one, outer function's power 2, so that's the first derivative we take. 2 comes down, the new power is 1. Then we multiply by derivative of inner function. Inner function is that natural log x right there, so let's copy it in. ln x, ln x. Then we just go from here. Derivative of natural log x is a 1 over x. So I have natural log x squared to start, plus 2 times x times natural log x times, now here we're doing the derivative, it's a 1 over x, which is nice. We get a cancellation going that way. So f prime at x, looks like we need a new line, becomes natural log x squared plus 2 natural log x. And that's a pretty decent simplified form, especially if we were in chapter 3. So our derivative is done. We're going to move on to the equation solving part next. But any questions at all, just taking the derivative? I find that's pretty tricky just on its own for this problem here. Okay, well, we said it's pretty simplified, and for chapter 3, it absolutely is. But in the context of doing applications to the derivative, any kind of optimization, finding maximums or minimums, because we're equation solving, we need to simplify even more by taking it into a factored form. And this does factor. We can take out a greatest common factor of natural log x. We'll divide right here where we see natural log x squared, leaving a natural log x, plus divides out from here, so this is just a +2. Now we can set this equal to 0, and so we're matching that step highlighted in yellow. We have f prime at x. It's natural log x times natural log x plus 2 as a group, set equal to 0. Reason for factoring is we can now split these factors and conclude this implies natural log x is 0, or natural log x plus 2 is 0. We can solve both equations, but this one is a pretty nice one. It's a nice mathematical fact that natural log 1 is 0, so we have an immediate conclusion. X is 1. Let's just say here, because natural log 1, a logarithm to any base at an input of 1 is absolutely 0 each and every time. So that's one critical number down already. This one takes a little bit more algebra, so let's subtract 2. We get natural log x is -2. Now to isolate x, you can make this an exponent to the base e exponential on both sides of the equation. That's a trick that we used on the last section notes, I think section 4.1 actually. If you do that, there's a cancellation going this way, and now we just have that x equals e to the power of -2. So let's make a summary. X equals 1 and e to the power -2 are the critical numbers of f. So once we have critical numbers, we can now go to the next step, which is look at the sign of the second derivative at those critical numbers to determine if they're positive or negative. But before we jump into that step, we need to compute the second derivative. So that's the natural step 2 of the second derivative test. Step 2 is find f double prime at x. So we have the function, we have the first derivative highlighted here in yellow is a pretty decent form. That would involve the product rule. I think it's probably easier to differentiate it right here on this first step. That would involve just the chain rule. I think that would flow a little bit better. So let me rewrite this just to make it more easily to track down here. F prime of x copied down, natural log x squared plus 2 natural log x. Didn't do anything new, just copied it from this line here. Now f double prime down below. We'll use the chain rule to start. We've already done this chain rule once when we differentiated natural log x squared here within the product rule. So same story here, you'll get 2 times natural log x times the derivative of natural log x, which is 1 over x, plus, now derivative of this with the constant multiple rule is just 2 times 1 over x. So that's our second derivative. We have to do stuff with that second derivative. So it's not one of those things where we would necessarily consider it fully simplified in this section. It pays off if we go a little bit further. Hang on, let me get some space going here for us. Because we have to plug values inside of the second derivative, the critical numbers, these two numbers. Anything we can do to make this a little bit more simplified is well worth it. Notice we have a common denominator of x on both of these. So one thing you could do is rewrite this as common denominator x, and then in the numerator, it's going to be 2 natural log x plus 2. You can go backwards by taking x divided into this first term and into the second term, and you just go right back to the last step. And I would say that's a pretty decently simplified form. Factoring out 2 is probably not worth it for this context of just plugging numbers in. So step 1, find critical numbers, first derivative. Step 2, well, we have to plug critical numbers into the second derivative, so we had to find the second derivative. And now step 3 is test and conclude. What I mean by that is we're going to take those critical numbers, test the sign of the second derivative to see if it's positive or negative, and depending on the value, we'll conclude we have a local minimum, local maximum, or that the test failed. And if the test fails, and you're told to use the second derivative test, that's all you have to say. Just say the second derivative test fails. You don't have to now do a lot more problem or a lot more analysis with the first derivative test. That's okay to just stop at that point. So we're ready to test and conclude. But to do that, we have to recall what was the original function in the very first place. So let's bring that down. It was x natural log x squared. So just as a reminder, let's put it here. F of x is x natural log x squared. So once again, we're looking at 3 functions. We have the first derivative, f prime. The second derivative is now very necessary for the next step. But when we say f at c is a local minimum or maximum, we're going back to the original function. So this is why it's really critical to label all of our functions as f of x and f prime or f double prime, just so that we're clear which function we're ever using. We have to jump through a lot of different hoops. So here are the critical numbers. We're going to take first f double prime at 1, that critical number. Here's f double prime. We simplified it to this stage. It's 2 natural log 1 plus 2 over 1. Natural log 1 is 0, so this is 2 times 0 plus 2 altogether. That means it's just 2. A pretty fast computation, but that means it's greater than 0. Actually, let me change my color coding here. We have that the second derivative at the critical number is positive. So an immediate conclusion is that f at that same critical number, 1, is going to be a local minimum. Let's plug in 1 to see what that minimum equals. F at 1 is 1 times natural log 1 squared. But that's kind of convenient again. Natural log 1 is 0, so this is just 1 times 0 squared equals 0, and this is a local minimum. So 0 is the local minimum of this function, x times the natural log of x squared. And that was just one critical number, so once 1 is done, we move to the next, e power negative 2. We take second derivative at e power negative 2. Here's where the second derivative is. So this becomes 2 natural log e power negative 2 plus 2 over e power negative 2. Let's simplify this to see what this comes out as. We have a cancellation going that way first. We don't have to do a lot of analysis on this. We just need to determine, is it positive or is it negative? So this becomes 2 times negative 2 plus 2 over e power negative 2. That means it's negative 4 plus 2, so negative 2 over e power negative 2. E power negative 2 is positive. E to any exponent whatsoever is a positive number. So that means we have a positive dividing into a negative. It's automatically less than 0. But that means we just found that the second derivative is negative on this one. We go back to the second derivative test, and a negative second derivative means at that critical number, e power negative 2, we have a local maximum now. So we just need to state that conclusion. So we'll say here, this implies f at, take the same critical number that you threw into the second derivative, e power negative 2. We need to find the value, so we go back to the function way over here. That's going to be e power negative 2 times natural log e power negative 2 squared. That's a local maximum, but let's continue to simplify it. Now the cancellation goes this way, so this is effectively just negative 2 squared. e power negative 2 times negative 2 squared gives us 4 times e power negative 2. And now we can conclude that that is a local max. So that's the maximum value for this function. And that's the complete analysis of finding minimums and maximums through the second derivative test. It does save some time. The function was just a little bit more complicated, x natural log x squared, versus our example 1 problem, which was just a polynomial. Now, if we double check our work on this, let's see how this works out. F of x is x natural log x squared. To kind of zoom in on this thing. But look, we do have a minimum at value looks like 0, and that's when we plug in a value 1. So that's the conclusion we're making here. At f at 1, we get a local minimum. It does look like a local maximum here. It's supposed to be 4 e power negative 2, so let's check that out. 4 e power negative 2 is about a 0.54, and we're matching those decimal expansions. So it looks like we do have the right values for local max and a local min for this particular function. Well, we can see that the max is 0.54134, but calculus went beyond what the graphing utility could do. If we needed to know the exact local maximum value, now we know it is precisely 4 times e to the power negative 2. So we needed calculus to make that determination. Well, that's the end of this optimization section, how derivatives affect the shape of the graph, mainly about local maximums, local minimums. We're going to see this material again when we're in section 4.7 on optimization, our big application section for this chapter. But for the end, before we get to that section, the next part of the notes we're going to take a look into will be indeterminate forms and L'Hopital's rule. Before we take a look at that next section, any last questions on this optimization section? Want to highlight that in the same way as before. What do you mean by the later end of 3? Do you mean the later end of example 3 down here? Sure, you can ask that question if you like. What question did you have on section 3.7? Well, those will definitely be on the test, yeah. Even simple ones like circumference of a circle, area of a circle. I mean, I feel like I know those formulas pretty well, but if I'm taking an exam, a little bit of anxiety might make that information just kind of disappear if I wasn't trying to memorize it. So yeah, any kind of algebra formula, geometry formula, whether it's volume, circumference, area, and so on, I absolutely will put those on the test. So that your focus is going to be mainly on the calculus, not on memorizing a bunch of random facts, like you have volume of a sphere, like you saw in one of those problems. So no worries about those. If there's weird formulas that come up, they will be provided. Other questions about that so far? Yeah, absolutely. You bet. Thanks for asking about that. Okay, let's now take a look into section 4.4. In a certain sense, 4.4 is kind of a nice section. We're reviewing certain kinds of limits. limits where we go off to infinity, or limits where we go to a finite number like on this one. But what's new about these kinds of limits are some of these limits were really rather hard to do that we just avoided completely when we were in chapter 2 doing our limits. Certain limits that were tough were things along the lines of, say, this. Trigonometry didn't even come up at all when we were on that section or that chapter 2 looking at limits in the first place. Some limits are just tough to think about, like e to the x over x, or even worse, x times sine pi over x, or worse still, x to the power of 1 over x. These are pretty random looking problems. But now that we have derivatives ready to go, there's a new idea that's going to help us take and evaluate a lot of these different kinds of limits. And the idea is the so-called L'Hopital's rule. L'Hopital is just a mathematician from hundreds of years ago that happened to buy this formula. Back in the day, mathematical formulas were commodities. So he bought the formula we're about to take a look into and just put it into one of his textbooks, which became majorly influential. And so this came to be known as L'Hopital's rule we're going to take a look into. Before we look at L'Hopital's rule, it's about indeterminate forms. Indeterminate forms could be things like 0 over 0. If 0 over 0 comes up when we directly substitute in a limit, it's considered indeterminate because 0 over 0 is not necessarily 1. It can be anything. It could be positive infinity, it could be 0, it could be negative infinity, or there could be a compromise for how the numerator and denominator are both heading towards 0, and it comes out as some finite number. So it's indeterminate in the sense that anything can happen here. If it arose from a limit, we need to analyze that limit really carefully. And L'Hopital's rule provides the framework for doing that kind of analysis. And there's more indeterminate forms. Here's the whole list. Any version of infinity, positive or negative, divided by any other version of infinity, that's indeterminate. We don't know what that's going to turn into. 0 times infinity, that's a weird one. Rules of algebra say that should be 0, but that's not necessarily true. It might be 0, or infinity might win here. It could turn out to be positive infinity. Or the whole thing could balance into a number like 5 or pi, square root of 12, anything random like that. Infinity minus infinity could be 0, or it could be positive infinity, negative infinity, or 13, and so on. 0 to a power 0 is not necessarily 1. Infinity to a power 0 is not necessarily 1 either. And 1 to a power of positive or negative infinity, anything can happen on that. It's not necessarily 1. So these are the kinds of things that we're going to be investigating in these notes. And they come up from things like these. Limit as x tends towards negative 5. We've done these kind of limits before, so this is in part review. But the major thing we're looking at now is, what kind of indeterminate form is it really? One way to do this analysis is to take a look into what happens to the numerator, what happens to the denominator separately as x gets closer and closer to negative 5. So we can write out as a shorthand, as x tends towards negative 5, that tends towards is going to be just this arrow we see here, same as we see in the limit down below. The numerator, x squared plus 4x minus 5. It doesn't equal something when we plug in negative 5, but it tends towards a value of positive 25 minus 20 minus 5, which is 0. So as x gets closer and closer to negative 5, just the numerator tends towards, gets closer and closer to a value of 0. And x plus 5 tends towards negative 5 plus 5, which is 0 as well. So to answer the question of what indeterminate form is this, the numerator is heading towards 0, the denominator is also heading towards 0, so it's the indeterminate form, 0 over 0. So I'll write that in shorthand as I and D, and these notes will stand for indeterminate. So let's define it up here as well by the definition. So it's an indeterminate form type 0 over 0. So the answer is not 0, it's not infinity, it's not 1. We have to do more analysis on the limit to resolve it. And this is one special case where we can do that, but for just about every other limit, almost every other limit that we do in these notes, we will need the so-called L'Hopital's rule, which we'll see on the next page. So now we know the limit, or excuse me, the indeterminate form is of type 0 over 0. And now we want to see what happens to this particular 0 over 0 indeterminate. The strategy for this one was to employ factoring. You can take limit as x tends towards -5, and the numerator factor this as x, let's go with maybe +5, x minus 1 divided by x plus 5. There's an immediate cancellation of those factors. This becomes equal to the limit as x tends towards -5 of the function x minus 1. Now, when we use direct substitution here, there is no possibility whatsoever for any of these indeterminate forms to exist. And even better, that function is now continuous at all real numbers. So we just use direct substitution. We get -5 minus 1 for a value of -6. So in the weirdest way possible, a 0 over 0, which is what you're looking at if you do the direct substitution, it is not infinity, it's not 0, it's not 1. There's a balance to how fast the numerator goes to 0, how fast the denominator goes to 0. They reach a compromise, and the whole thing is just getting closer and closer to a -6 altogether. So that's I'll just leave that highlighting there, that doesn't hurt. That's the idea with indeterminate forms. More analysis has to be done to resolve the limit once we know it's indeterminate. Well, again, this problem was part review, part preview for L'Hopital's rule. Next, we're going to take a look into that L'Hopital's rule, but any questions at the moment? Okay, let's take a look into that rule next. Let's maybe take this along with this. I have a feeling we're going to need this later on in the notes. So let me screenshot it down as well. So here's L'Hopital's rule. It's a pretty big statement. So let's go through it in pieces. We say f and g are differentiable functions, which fits this chapter. This is applications of the derivative. G of x is not equal to 0 on some interval that contains a. The role of a is that's where the limit is heading towards. X is tending towards a. Now it says suppose that the limit of f is 0 and the limit of g is 0. When we say that, because we're looking at f of x over g of x, we're thinking indeterminate type 0 over 0. Or the limit as x tends to a f of x is positive or negative infinity, and same for g of x. That means we have an indeterminate form of type either positive or negative infinity divided by either positive or negative infinity. That's really 4 different indeterminate forms, depending on which sign you pick for the numerator and denominator, 2 possibilities for each. So any one of those is indeterminate. So if you have one of these 2 indeterminate forms, then here's how you resolve the limit. It's a pretty amazing trick. It's all about how fast does the numerator go to 0 and the denominator go to 0, or how fast does the function f go to either positive or negative infinity, and same for the function g. If we look at the rates at which they head towards those values, then we're doing that limit there. So we can transfer from a limit of f of x over g of x to the limit of f prime of x divided by g prime of x. So this right here is the major idea of L'Hopital's rule. One thing to keep in mind is in L'Hopital's rule, you must have 0 over 0 or plus or negative infinity over plus or negative infinity indeterminate forms. These are the only one that works, which is kind of unfortunate because recall, let's put it down here just for reference. There's a whole bunch of indeterminate forms. So what do we do if one of the other ones show up on this list? We have to do something to the function algebraically so that it becomes a 0 over 0 or an infinity over infinity. Then we can use L'Hopital's rule. So that's the whole idea of L'Hopital's rule. We take the derivative of whatever is in the numerator, divide by the derivative of what is ever in the denominator. Another really big warning that's easy to miss when we see L'Hopital's rule is this is not a quotient rule. We're taking the derivative of f divided by the derivative of g independently of one another. We're not using the quotient rule altogether and just differentiating the whole fraction. So just differentiate the numerator, differentiate the denominator, and our work is done. So we'll see how that goes on example number 2 down below. It's the same problem that we started off on example number 1. We know already it's a determinant of type 0 over 0. That means L'Hopital's rule applies. It can be used on this. So let's give it a try. We'll say it's equal to limit as x tends towards -5. And one little strategy to use in the notes is we're about to use really a pretty gigantic theorem. This is a big tool to resolving a limit. Because of this tool that we're using on the limit, this is something that I usually put down the notes to alert anyone that's reading this again. So if you came back to these notes, each time I do use L'Hopital's rule, I'll put an H above the equality to say I have just used L'Hopital's rule. So if you're wondering what in the world happened to that limit, the H there is a hint. I encourage you to do it in your same work, but it's not required. It's really just a note-keeping device. So following the idea of L'Hopital's rule, we take the derivative of the numerator, that's going to be a 2x, plus 4. Again, not quotient rule, just strictly divide by the derivative of the denominator, which is 1. That's a nice derivative. Now we resolve this limit, 2x plus 4. This is a different value than when we cancel the factors. So let's see what happens with this one. When we plug in -5 into 2x plus 4, we get 2 times -5 plus 4. So that's going to be -10 plus 4 for a value of -6 altogether. Let's take a peek. I forgot what we did before. Hey, we got -6. There was a different way we did this limit. The work looks different. But L'Hopital's rule resolves to the same exact value. And already you can imagine this is a pretty nice trick because sometimes factoring things is not always very nice. You might need the quadratic formula. It might be hard to determine what it factors as in trial and error. But if indeterminate form 0 over 0 comes up, this gives you options. Just hit it with the derivative, numerator and denominator, through L'Hopital's rule, and we've got the same exact conclusion. So that's the essence of how L'Hopital's rule works. And what we'll be doing on the rest of these notes is just practice using these ideas for further examples down below. Any questions at all, seeing how it went with this very first run? Okay, so big idea with L'Hopital's rule. I feel like this deserves to be in a box as a strong component of it. You have to have those two indeterminate forms. If it does, treat the numerator and denominator as separate functions. Forgot to highlight that one. Differentiate them independently of another, and if this limit got simpler, then evaluate it using the ordinary tricks from chapter 2. Here we just use continuity and direct substitution. We've plugged in -5 directly into x for the function. So trying this out again, here's another view of L'Hopital's rule. This one's a little bit different because I know what the denominator function is, but we don't know what the numerator function is. We just know that it's this function here, plotted in green. So this one is a bit of a challenge in a certain sense. We have to think about this one geometrically in part as we go through L'Hopital's rule. I think the major reason that I put it here on these notes is it's also in the homework as well. So this is to help out with the homework. I felt like this is a decently challenging problem. So we have the graph of y equals f of x here. And more than just the graph, notice we have a point of tangency right at 3, and a tangent line equation, y equals 4/3 x minus 4. So this is a tangent line equation. But because it's a tangent line equation, if you take the value 3 that we see here, where the point of tangency occurred, and look into, say, f prime at 3, if we take the derivative of f at 3, that's going to always be equal to the slope of the tangent line to this curve when x is 3. Here is the tangent line equation, and that slope is exactly 4/3. So we actually know a value of the derivative just from this graph. That alone, I believe, is pretty tricky, that we can take the slope of the tangent line right here, relate it to the derivative. We constantly say that the derivative at a number is a slope, the slope of the tangent line, but seeing it this way sometimes feels kind of new. So that's another reason for doing this problem here. It's in part review, refreshing these kind of ideas, and seeing it through the graph. Now back to that limit. Even though we don't know the function f of x, we are taking the limit as x goes to 3, where the exciting thing happens with the tangent line. We have f of x up above, x squared minus 9 down below. But let's also look what happens as x tends towards 3. The numerator f of x tends towards f at 3, but f at 3 is 0. So we have 0 in the numerator. Now, how about the denominator, x squared minus 9? Well, x squared minus 9 as x tends towards 3 becomes 3 squared minus 9. Also 0. So this entire limit that we're looking at by our analysis here is indeterminate of type 0 over 0. That's good in a way because it tells us we can use L'Hopital's rule on this particular limit. It was 0 over 0 or any flavor infinity over infinity for which we can use it. So we're ready to hit it with L'Hopital's rule. I'll put H here once again to say we are using L'Hopital's rule at this stage. Take the limit as x tends towards 3. I'll color code it differently because we already put f in green, so we should stick with that. What we do is we take the derivative of the numerator, so here it is. We have f of x up above. I don't know the derivative because I don't know the function, so we can do that though. We'll just call it f prime at x. We took the derivative of the numerator. For the denominator, not as bad, x squared minus 9 has derivative 2x. So that's what it would look like so far. And notice when we differentiate the denominator, as x tends towards 3, the denominator now heads towards 6. This is no longer indeterminate. So let's use direct substitution. As x tends towards 3, the numerator is going to tend towards f prime at 3. The denominator is going to head towards 2 times 3. Through the graph in our initial analysis, because we had a tangent line equation, we take the slope there, and that already provided for us that the derivative of f at 3, our new numerator, is exactly 4/3. So we get 4/3 up above, and we're dividing it all by just a 6. Which means we have a value out. We just need to simplify this. This is now really 4/3 times the reciprocal of 6, 1 over 6. And more simplification, we get 2 when we cancel across numerator denominator. So this is 2 over 9 altogether for the value of the limit. So this problem here, again, it's pretty weird. There's one in the homework, so I felt like we ought to do it for the notes just for a good idea of how it should go when you try it out again in the homework. But the really big essence of this problem was really more about this. Going from the function here to the derivative of the numerator divided by the derivative of the denominator. Once you know, you have one of those good indeterminate forms for which L'Hopital rule applies. Well, we did it. That's the conclusion to our example number 3. It has a lot going on because of the tangent line equation analysis we had to do here. Any questions about either one of the elements on this one? Okay, well, now we're on to example 4. It's the last example for these notes. On example 4, our goal here is to just calculate the limits on each one of these exercises that we previewed at the start of the notes. Let me put here for reference, here are the indeterminate forms. And a reminder, L'Hopital's rule only applies to those kinds. Only these work in L'Hopital's rule. So these are the common ones that occur, but we're also going to see in example number 4, the other types that can occur as well. So for each one of these, one thing we have to determine is, can we just do the limit outright by direct substitution? Sometimes you really can, and this section's homework, sometimes L'Hopital's rule isn't required at all. So always try to look for an easier method. The problem should start off with an analysis that looks like this. See where x is going towards. Go like that. X is heading towards 0. So I'll say as x goes towards 0, the function in the numerator, 1 minus cosine x, will tend towards 1 minus cosine 0. Cosine 0 is 1, so this just becomes 1 minus 1 for a value of 0. And that's the numerator portion right here. It looks like L'Hopital's rule might be able to be used. And it looks like it's almost a definite with what's going on in the denominator, because x plus x squared also tends towards 0. This tells us it's indeterminate of type 0 over 0. But that's one of the good indeterminate forms. It means we can now proceed to the next step of hitting this with L'Hopital's rule. We have two functions. Another reminder, because it's easy to forget, this happens sometimes on homeworks and even on exams. Recall in L'Hopital's rule, it's not the quotient rule. Never forget quotient rule, but make sure you don't use it in this case. We are going to say, by L'Hopital's rule, it's a limit as x goes to 0 of, take the derivative of the numerator. That will give us negative derivative of cosine x, which is negative sine x. The constant in front just goes to 0. And derivative of the denominator is going to be a 1 plus 2x. So let's simplify this just a touch. This is limit as x goes to 0 of sine x, 2x plus 1. And well, as x tends towards 0, the denominator tends towards a 1. We get a 1 by direct substitution. So it's no longer indeterminate if we have a constant in a denominator. As x tends towards 0, the numerator, we get a 0 altogether. So now we're using direct substitution. This becomes, through continuity, sine 0 over 2 times 0 plus 1. This becomes 0 over 1, but that's absolutely determinate. That's exactly equal to 0 no matter what. So now the limit is done. And like we mentioned at the start of these notes, we didn't do anything remotely like this when we were looking into limits in chapter 2. We did as many limits as we could, but we were actually very limited in what we could deal with. Mixing a trig function with an algebraic one in this kind of way, I think this was done in section 3.3 in the reading in a much more painstakingly done method. But L'Hopital's rule makes this really fast. We can use continuity for this cleaned up function and get a conclusion almost immediately. So that's the big selling point of L'Hopital's rule. Limits that were a total mystery from before are now, just by applying the derivative through the rule, very, very fast to get through. So we have several more just for more variety to see what happens for the next ones. Any questions on part A before we take a look at the next? Okay, well, let's take a look at what happens now this time as we take a limit as x tends towards infinity. If the limit exists here, we'll get a horizontal asymptote. In chaps, so in L'Hopital's rule, it's just making the limits into a derivative without the rules. Yeah, that's absolutely right. I mean, we still use the rules for the thing in blue. If the thing in blue was a fraction, it would have used the quotient rule. It could be a chain rule that comes up and so on. But the idea is we're not taking the derivative of the function in its totality. With what's circled there, that would have been a quotient rule. So we take independently just the thing in blue and differentiate that using the rules of the derivative. And independently, as a whole new function, on its own, differentiate that one. So yeah, we're not using the quotient rule like we would normally. We're splitting into two, just looking at one independent of the other. Does that make sense with that question there? Gotcha. And yeah, taking another look into just L'Hopital's rule itself up above, that's a kind of idea that's being stated right here. Whatever's going on with the function f, if f happened to be, say, e to the x divided by x in that limit there, then we go to f prime over here, it's still a quotient rule in that case. But what's being conveyed here is that overall, when you see this formula for L'Hopital's rule, that formula itself is not using quotient rule. This is like a brand new formula in its own right. Yeah, this is an easier way to do limits, but only when the indeterminate form comes up. So 0 or 0 must come up, infinity over infinity must come up. If those two limits or two indeterminate forms do not come up, and you use this rule, more likely than not, you would get the wrong answer for the limit. So when it works, it's spectacular. It makes the limits a lot easier to get through. But if we try to apply it where there's no indeterminate form of these kinds, it doesn't work at all. You could get random, nonsensical answers. So yeah, the answer to that question is only related to indeterminate form questions. It will resolve all of them on this list here, but if one of these other ones not highlighted comes up, we have to rewrite the function, do something algebraically, so it becomes 0 over 0, infinity over infinity, and then we take that step where we differentiate numerator and denominator as independent functions. Other questions about that so far? Okay, let's try out the next one to see how it goes. This time, x is getting larger and larger, heading towards infinity. So we can say in our initial analysis, as x tends towards infinity this time, e to the x, we need to know what that goes towards. This one also goes towards infinity. The way I thought about this one is, well, it's an exponential function. It's literally growing exponentially, right? But another way to think about it is going back to section 2.6. Section 2.6 had a series of really important graphs like tangent inverse or say e to the x. And on the e to the x function, here's what the graph looks like. As x tends towards infinity, e to the x also goes towards infinity. Notice how sensitive that is. If you're going towards negative infinity, you're heading off to a horizontal asymptote, and in that direction, the limit is 0 for that horizontal asymptote. But because we're going off to infinity, we now have an infinity in the numerator, and same thing that's happening down below, 2x cubed. Well, x cubed gets larger and larger and larger as x heads towards infinity. So double it, and it still tends towards infinity. And so these two parts right here tell us it's indeterminate, infinity over infinity, which means we're on this version with plus infinities on both numerator and denominator. So anything can happen to this one. The limit could exist as a finite number, or it could be 0, infinity, negative infinity, and so on. Probably not in negative infinity, since these are both positive values that we got. That does require further analysis, so on the next step, we'll hit it with L'Hopital's rule. But L'Hopital's rule is going to be fast to apply to this. We are just taking really quick derivatives because it's not the quotient rule. This becomes a limit as x tends towards infinity for the derivative of the numerator. That's just e to the x, so it's done right at that stage. Divide by the derivative of the denominator, that's just going to be 6x squared. And now that derivative is done. It's a slightly different limit, but notice what still happens. E to the x, it still goes off to infinity. 6x squared, as x gets larger and larger, still heads towards infinity. So this is still indeterminate of type infinity over infinity. So this is indeterminate infinity over infinity. It's kind of weird, and this can happen with L'Hopital's rule. And one thing that's kind of interesting and almost magical about L'Hopital's rule is you can keep on applying it. If we're still indeterminate once we used it once, use it again and hope for the best. So we just hit it with L'Hopital's rule yet again. Take the limit as x tends towards infinity. Taking that limit to the numerator means differentiate the numerator function on this step 2. Still e to the x. Differentiate the denominator function. Now it's 12x. And that's the new function. Notice this game cannot continue forever because eventually it's going to be a constant in the denominator, and a constant, as you take a limit as x tends towards infinity, stays that number. So we're going to lose that infinity in the denominator and the ability to use L'Hopital's rule eventually. But this one is still indeterminate of type infinity in the numerator. 12x, as x goes to infinity, 12x goes to infinity. We're just multiplying whatever number you put in by 12. So we hit it with L'Hopital's rule yet again. Take limit as x tends towards infinity. This can happen in the homework where you have to use L'Hopital's rule multiple times. You get e to the x, just as before, but the derivative of the denominator is now 12. And at this stage, it is no longer indeterminate. We're taking the limit as e to the x of e to the x as x goes to infinity. We already know e to the x goes to infinity. And dividing it by 12 doesn't change that conclusion. It's just a constant. If the thing in the numerator just gets larger and larger and larger, heading towards infinity, that means the result on this one is infinity altogether. This limit didn't exist, and the reason being, it happened to just blow up towards positive infinity. So this one's a weird one. This can happen in the homework as well, where you use L'Hopital's rule maybe a bunch of times until it resolves into a nicer limit like this one here. So that's 2 L'Hopital rules down. Any last questions on getting through part B? Okay, there's kind of more to the story of what is happening in part B. It turns out if you put in an exponential like this, e to the x, 5 to the x, anything along those lines in the numerator, and you're heading off towards infinity, it doesn't matter what polynomial, specifically polynomial, you put in the denominator. This could have been 2 to the power of 2 times x to the power of 300. In the short run, the denominator grows really, really fast, much faster than e to the x. But in the long run, as x gets larger and larger, the exponential growth eventually takes over. It's heading towards infinity much faster than any polynomial you put in there, no matter what degree. And so the conclusion to this of an exponential divided by any degree polynomial is always infinity, no matter what. So that's just telling you the growth rate at e to the x is always just completely dominating, destroying the growth rate of any polynomial we put down. But here's a new one, but notice the direction change. E to the x is still in the numerator, but now we're taking a limit as we go towards negative infinity. From what we did in section 2.6, we know that that limit is now 0. change one small thing, go from infinity to negative infinity, and the outcome is just totally different. So this one is a different kind of problem. Let's carry this down as we go. So when we do the analysis on this one, we have e to the x in the numerator, and we can say as x tends towards negative infinity, e to the x tends towards 0 altogether. And what about the denominator? X to the power negative infinity, or excuse me, x itself will tend to, it's kind of redundant, if x is tending towards negative infinity, x is tending towards negative infinity. Actually, let me bring this up just a little bit. This is one where we have to be really, really careful out of nowhere. It's quite a bit different than part B. Part B, we had indeterminate form infinity over infinity. That was this one right here. Part A had 0 over 0. But if you have 0 over negative infinity, it's not on the list. This is not an indeterminate form whatsoever. We can do this limit in a normal way. In fact, if you use L'Hopital's rule on this one, let me see, if we use L'Hopital's rule, I think we luck out and we get the right answer, but that's not a foregone conclusion. It's just as well we could have gotten the wrong answer for our arbitrary function. So let's say here, just for the warning on this, 0 over negative infinity is not indeterminate, which means L'Hopital's rule cannot be used. And that deserves an exclamation mark. So what's really happening with this one? The numerator is getting closer and closer to 0. In the denominator, we're dividing by something that's getting larger and larger negative. For example, we already know that the limit, as x tends towards negative infinity, of 1 over x is just 0, because that's the horizontal asymptote for this function. If you put in the numerator something that's also heading towards 0, quite a bit faster, the whole thing is still heading towards 0. The value of this limit is still just 0 altogether, and no further analysis actually had to be done. We just had to know that if you're dividing by something like x, as you go to infinity, it's already heading towards 0. Multiplied by e to the x, which is also heading towards 0, means this function, e to the x over x, goes to 0 extremely fast, and that's all we have to do on this one. So watch out for these. Sometimes in the homework, L'Hopital's rule cannot be used. And I think there's a problem in the homework where if you did use it, you wouldn't get the right answer anyways. So we have to be very, very cautious. So part C is just kind of a random one mixed in, just for that word of warning. The next part down below is going to be a L'Hopital rule type of situation, but it's one where we have to clean it up algebraically first before we even get started. Before we take a look at part D, any questions at all on the part C version? Okay, let's take a look into this next one. In part D, we're taking the limit as x tends towards infinity of a product this time, x times sine pi over x. So we have a function here, a function here, and now we can say as x tends towards infinity, this is redundant, but it's going to follow the structure of the function here. As x tends towards infinity, x tends towards infinity, so there we go, we set it. Let's look at the other factor, sine pi over x. Just like on the last limit that we looked at here, 1 over x and the limit is 0. Likewise, we take pi divided by x. As x gets larger and larger, positive infinity or negative infinity, that just becomes 0. So sine pi over x gets closer and closer to sine 0. but sine 0 is 0. Now to analyze the form that we have, this means we have form indeterminate, type infinity, times 0. It's indeterminate of this type now. I switched the factors, but whether you put the infinity first or the 0 first, it's still that same indeterminate form. And that's really problematic for us because you still cannot use the L'Hopital's rule in this setup until it looks like either one of these, and 0 over 0, infinity over infinity. But if an indeterminate form comes up, like 0 times an infinity, like that's occurred on this one, we can rewrite the function and still use L'Hopital's rule. So that's the idea of this one, rewrite before L'Hopital's rule. And here's the trick that we can make to have it all work. Take the limit as x tends towards infinity. We need to throw something into the denominator. L'Hopital's rule is about fractions, really, a numerator versus denominator. And the simplest function to put in the denominator would be x itself. It's to x power 1. So in the denominator, it's x to the power -1. So there it is. It's now tucked away in the denominator. And in the numerator, it's sine. We can leave it pi divided by x, but we're about to differentiate. It's a little bit easier to visualize the derivative in this form, pi times x power -1. So it's still sine pi over x, and it still goes to 0. But now we have a new function, x power -1. So we can say, as x tends towards infinity, we have sine pi over x. Let's just write this down just for the sake of keeping it all in one spot. This still tends towards 0, but x power -1, which is really just a 1 over x, as x tends towards infinity, this also tends towards 0. But that's good news for us. That means the moment we took x and in a valid algebraic way tucked it away into the denominator, we got to that indeterminate form. It's indeterminate of type 0 over 0. That's one of the two and only two types, 0 over 0, infinity over infinity, for which L'Hopital's rule works. And so now at this stage, L'Hopital's rule does apply. So let's hit it with L'Hopital's rule. We'll take the limit as x tends towards still infinity. We take the derivative of the numerator. It's a chain rule where first we differentiate sign. It becomes cosine pi times x inverse times the derivative of pi times x power -1. Then we multiply that, or excuse me, we divide all of that by the derivative of the denominator, x power -1 prime. Let's do the derivatives on the next step. We can now say that this is equal to limit as x tends towards infinity, cosine, I'll rewrite this as pi over x like before, times, you can use a constant multiple rule. I write this as pi times derivative of x power -1 is negative x power -2. And same derivative of x power -1 is negative x power -2. And that means there's a amazing cancellation on this. The negative x powers and -2 are just gone. And now we're taking the limit as x goes towards infinity of pi times cosine pi over x. And we're essentially done at this stage. We did a very similar limit over here. As x tends towards infinity, pi over x tends towards 0. We'll use the same idea over here. Yes, if you're, say, multiplying like this by the constant multiple rule through the derivative, pi stays as pi. If you did it like this, though, pi plus x inverse and differentiate, you would get 0 minus x power -2. So here, when you do the derivative of the constant, it would go to 0 in that case. But constant multiple rule, anything multiplying by the function, it just carries down in that kind of way. Yeah, exactly. Just a weird looking constant when we see it. So last stage on this one, as x tends towards infinity, pi over x goes towards 0, and we get pi times cosine 0. Cosine 0 is a 1. So the whole thing just turns into a pi, and then right at that stage, we're done. Even though it was an indeterminate of, say, infinity times 0, infinity times 0 could either be 0, it could be an infinity, or it could compromise. This time it turned into be just pi itself. And so that's the way these indeterminates are truly indeterminate. If anything like this comes up on a list when we're analyzing a limit in this way, we get any one of those indeterminate forms, anything is on the table. Any number or value, infinity, negative infinity, could come out. Well, we've got one more to take a look at, but any last questions at all getting through any of these? Okay, well, here's the question is, what is this used for? Well, this could be used in a lot of different kinds of applications. If for any kind of reason you're modeling a function that looks like sin x times sine pi over x, you want to know what's going on in the long term as x tends towards infinity, you would have to use L'Hopital's rule to resolve this kind of thing. But probably the more honest answer of what any of this kind of stuff is used for is this is really kind of a building block that gets us into Calculus 2. And for the last moment of our time, let's take a look into that. Let's go to, let's see, I never taught Calculus 2 yet in Canvas. So let's go back to, I think the Moodle website is still open, even though we haven't used this in years now. And I want to take a look into, to give a good answer for these kind of limits, this content down below here. Okay, Calculus 2, Spring 2025. And if you go all the way down into chapter, say, 11.9, or even better, Taylor-Maclaurin series, here's where we have some really weird stuff that comes up. In Taylor-Maclaurin series, we're going to be able to rewrite taking some really crazy limits as something n goes to infinity, different kinds of functions such as the hyperbolics like we studied, and trying to get down to a particular table. Here's a good one. And the cosine function, sine function. A lot of these functions, if you look at the textbook, it's called early transcendentals. And this is what a transcendental function looks like. Cosine is the world's most bizarre function as a formula. If you wanted to put down a formula and not ever use the unit circle where you're picking an x coordinate and a y coordinate, this is the formula for cosine. It's an infinite sum, infinitely many terms, all just brought down together to form out this weird, wacky formula. And the way we determine the domain is we have to take some really complicated limits. Here's one version of that. And occasionally when we do these limits, I think I have another example where this occurs. Let's go to maybe the integral test. Sometimes when we do these limits, I think I have a good one here. L'Hopital's rule just comes right out of these. So where is L'Hopital's rule? I know it's in here somewhere. Might not find that right away. Let's see. I haven't used L'Hopital's rule yet on this one, but somewhere in these notes, when you go through Calculus 2, we're trying to come up with a good formula for cosine. L'Hopital's rule has to be used for the kind of limits we're using. So the best answer to what is this stuff really used for is all of it comes back. Chapter 2, section 4.4 as well, in particular, in the Calculus 2 setting, where we're getting into the concept of series. And then finally, Taylor series and Maclaurin series tells us, what is the cosine function really? I think I might have a table down below. Let me take a look into another one. That was 1110. Here's part 2 to that. And yeah, this is the table I was trying to look into. Here's some of the transcendental functions like e to the x. Binomial series is there as well. All of these kinds of things, to really study them, we have to have a really good handle on working limits. And L'Hopital's rule gets involved with plenty of these kinds of things that come up down the line. So L'Hopital's rule, again, is one of those things that doesn't go away. Gets used quite a bit in Calculus 2, gets used in Calculus 3. And yeah, I'm going to be doing it in the same way for Calculus 2. I don't think it's at the same time, but I'm going to be doing it in the fall semester, fully online with an in-person section as well. And we're just going to pretty much just build off of what we end on when we get through the Calculus 1 course as well. I believe there is an in-person section as well for Calculus 2 in the Idaho Falls area that I'm teaching. I think it goes Monday, Tuesday, Thursday, and if I remember correctly, I think it's from 6 p.m. to 7:10. And yeah, it's going to be a full semester class, so we won't be going twice the speed like we are for the summer class. It's really kind of brutal when we're going twice the normal speed. It'll be done at a normal pace. So we'll usually just do about a section to maybe 3/4 of a section per day. Whereas this class, we've been doing anywhere between 1 to 2 full sections per day. It's really quite a rapid pace to get it done in 8 weeks. And speaking of which, we didn't quite get through section 4.4, but that's okay. We're going to leave this last problem here as just another warm up when we come back on Monday's class. We'll do this final problem, think about L'Hopital's rule a little bit more, and then go into the optimization section 4.7 here. So I'll be moving this down into the next week. So this will be a pretty good stopping point for us today. Yeah, we'll have a class this time on Monday, since this time, no big national holiday, no exam that we're doing on our next week. So this will be once again, our first full week, but then just a week after, we're going to take Monday off again because that's the official day for exam 3, which means also on this weekend, after grading exams, probably on Saturday or Sunday, I'll be posting the definite exam 3 information to tell you what sections are included, as well as post some review problems as well. Well, any other questions at the moment before we call it a night? Okay, well, have a great night, Caleb. Thanks for making it in today. On next Monday's class, and yeah, we'll actually have a Monday class. It's been a while. We're going to finish off 4.4 and 4.7. So these sections and assignments are going to move here with adjusted due dates. But have a great night, have a great weekend, and we'll be back to it next week. Yeah, that's right. We're going to go from section 4.4 into 4.7.